Hello, this is Jude Socrates, and today's video is about the span of a set of vectors in R2. So in section 1.2, we write the definition for the span of a general set of vectors. So let's bring back that definition. The definition says that the span of a non-empty set of vectors S, written as v1, v2 through vk, and these vectors are from Rn, is the set of all possible linear combinations of the vectors in this set. And so we write this symbolically as the span of S, the span of the vectors v1 through vk, are x1 v1 plus x2 v2 all the way through xk vk, where x1, x2 through xk are all real numbers. So because we can also let each coefficient be 1 and everyone else be 0, we will just get either v1 or v2 individually. And so v1 through vk are all automatically members of the span of S. Now, if all the coefficients are 0, then of course that linear combination is also 0. So therefore, the 0 vector is also a member of the span of any set of vectors. Now, the simplest case would be when S contains only one vector. So S is just the vector v, in which case the span of S is simply all multiples t times v, where t, of course, is a real number. So we can just think of it as all the scalar multiples of v. But even in the simplest possibility, there are two cases. First, what happens when v is just the 0 vector? Well, we saw from the first section that any multiple of the 0 vector is still the 0 vector. And therefore, we can say that the span of the 0 vector, which is all multiples of the 0 vector, is just the 0 vector. So let's write that over here. So we have that the span of 0n, all the multiples of 0n, is still just 0n. That's not very exciting, is it? It's downright boring. So of course, the other case where v is not the 0 vector is a lot more exciting. So now let's consider case 2, where v is not the 0 vector. What does span v look like in this case? And this is where we are going to go to a website. It is called GeoGebra. To find it, just go to your web browser and type in GeoGebra Classic. There's of course a new version of GeoGebra, but personally I prefer GeoGebra Classic because it is better when dealing with three-dimensional objects, which we will see very soon. So this is what the welcome screen for GeoGebra Classic looks like. So you have the two-dimensional Cartesian coordinate system, you have the input box over here, and there are some icons over here that we'll talk about later in the future. Today, we are going to input vectors. So to do that, you type in the command vector, followed by parentheses. And when you type in the left parentheses, the right parenthesis also shows up. But inside the parenthesis, you need another pair. So we will type in another left parenthesis. And again, the right one comes for free. We will type in the vector 5, 2. And there it is. Here's the vector 5 on x, 2 on y. And of course, it's drawn in standard position where the tail of the vector is at the origin. So this is the default appearance of vectors in GeoGebra. One of the things I like to do is change the color. So we can go to settings. And then on the right side, we see color. And we can pick my favorite color, which is of course red. And there you see it. So now U is this vector, and it's red. We are studying the span of a set of vectors. So let's take a look at scalar multiples of U. Okay, so we can multiply U by any scalar that we want. So we can type, for example, W1 will be 2 times U. And there it is. So again, it is in standard position, and it goes to the default color of black. So there is W1, and you can see it's also labeled as W1. Let's make W2 be 3.5U. So there we go. It's now off the screen. Let me close the properties section. It's still off the screen. So let's make a shorter vector. How about W3 will be, how about negative 1.5U? Okay, so now it is pointing in the exact opposite direction. So where are we going with this? We want to look at every possible scalar multiple of our vector u. We are looking at 3 scalar multiples of the vector u, along with the original vector u, of course. And we said that if you multiply u by 0, you'll just get the 0 vector, which I suppose is part of the picture. Okay, now, if you keep filling up the screen with more and more vectors, so how about negative 1.75u? There you go, we get still another vector in the span of u. Now, I think it would be reasonable to say that when you put all of these vectors together, you form what you would intuitively call a line. And of course, that is what we're going to call the span of this set of vectors. After all, the name of the subject is linear algebra, so it should be no surprise that lines will show up in our study of linear algebra. So now that we have seen the picture, let's do the algebra part of linear algebra. We have for our example, u is 5, 2, and we are writing this in what's called a matrix. And in this case, it is a very small row matrix. So there are only 2 numbers, and we're going to do this so that we can take advantage of the computational power of the software which I'm using, which is called Scientific Notebook. So by the definition, the span of u is all the multiples of 5u, so we write t times 5u, and we can bring the t inside the vector, because that's a scalar multiple, so it's all the vectors 5t, 2t, where t is a real number. We want to find the equation of the line, whose picture we saw in GeoGebra. So to do that, let us call the vector 5t, 2t by a name. Let's call it xy. So xy equals 5t, 2t. Now, 2 vectors are equal when their components are equal. So of course, we can write this as x equals 5t and y equals 2t. So we have 2 equations, and they both involve t. So of course, we can solve for t. Solving for t, we get 2 equations. T will be x over 5, and t is also going to be y over 2. Okay, so we have 2 equations for t, and of course, that means that x over 5 has to be equal to y over 2. So thus, we get, solving for y will be 2x over 5. And of course, that looks like a good equation for the line that we saw in GeoGebra. So here's that picture once again, and because u is 5, 2, our line goes through the point 5, 2, and of course the slope, since it passes through the origin, is 2 over 5. So the equation y equals 2/5 x is indeed correct. So let's move on now to the case where S contains 2 vectors. So let's say those vectors are u and v. So now span of S will be all vectors r times u plus s times v, where r and s are real numbers. In other words, these are all the possible linear combinations of u and v. So let's add on to our previous example. We had u, which was 5, 2, and now let's make another vector. Let's call it v. That'll be negative 1, 4. So let's go back to GeoGebra now, and let's make many combinations of u and v. So let's start over. I kept our old vector u, and I input a new vector v, negative 1, 4, and I colored it blue. So as we make more linear combinations of u and v, we will see the original vectors over here. So let's make w1, which will be, how about just u plus v? Aha, so there's w1. w2 will be, how about v minus u? So that's a linear combination because that's 1 times v plus negative 1 times u. And there's w2. How about w3 will be u minus 2v? Aha, now it's pointing down and to the right. Let's make w4. We can type in v over 2 minus 3u over 2. Whoops, we have to move the right cursor. Minus 3u over 2. That's better. So that is a fractional linear combination of u and v. And now it's pointing down and to the left. How about the last one? w5 will be negative 2v over 3. So remember to use the right arrow to get out of the fraction, minus u. And there is our fifth vector. So those are 5 linear combinations of u and v, along with the original vectors u and v. So they seem to be pointing in all sorts of directions. So where are we going with this? We want each and every linear combination of the two vectors u and v. We're only looking at 7 of them. Okay, so what if we started filling up the screen with more and more of these vectors? So there will be arrows pointing almost everywhere. So that makes us wonder, well, is it possible that maybe if you want any vector in R2, any arrow in R2, is it possible to create that arrow as a linear combination of u and v? So let's think about that question. So the question we now want to answer is it possible that every vector xy in R2 is a linear combination of u and v? So we want to solve the equation. Can we make xy equal to ru plus sv, where r and s are two real numbers? Given xy, can we solve for r and s in that equation? So let's write down that equation. So here's that equation. Given xy, can we solve for r and s such that xy is ru plus sv, which is r times 5, 2, plus s times negative 1, 4. The first step to solving this equation would be to simplify this linear combination. So we get for our first component 5r minus s in the first component and 2r plus 4s in the second component. So we are solving for r and s in the system. We want x to be 5r minus s and y to be 2r plus 4s. So we have a system of two equations in two unknowns, r and s, and we want to solve for r and s, hopefully in terms of x and y. So to solve the system, let's apply the addition method that we see in basic or intermediate algebra. What we have to do is multiply each equation by a suitable non-zero number so that the coefficients of one of the variables will cancel out when we add the corresponding sides of the two equations together. So in this case, if you want to eliminate r, then we can multiply the first equation, let's say, by negative 2, and the second equation by 5, so that we'll get negative 10 and positive 10. That will cancel out to 0. So we will get negative 2x equals negative 10r plus 2s, and 5y equals 10r plus 20s. So when we add them together, we will get negative 2x plus 5y equals, that should be r, equals 22s. And so we can solve for s, and we will get negative 2x plus 5y divided by 22. So if we were back in basic algebra, now that we know s, we can solve for r by plugging in s using either x or y. But since we're already at it, why don't we just eliminate s from our two equations, just like we eliminated r? In this case, it's actually easier to eliminate s, because all we have to do is multiply the first equation by 4, so that we will get negative 4 cancel with positive 4. So we get 4x equals 20r minus 4s, and same second equation, so let's just copy it, y equals 2r plus 4s. So we get, adding them together, 4x plus y equals 22r. And so r is going to be 4x plus y divided by 22. So there we have it. We were able to solve for both r and s given x and y. So that tells us that every vector xy is part of the span of the two vectors u and v. But to make sure, let's check that our answers work. So our solutions were s equals negative 2x plus 5y over 22, and r is 4x plus y over 22. So let's check that when we plug in r and s into this equation, we will get the vector xy. So let's simplify this. We want the linear combination r times 5, 2. Here is r, and s times minus 1, 4. So let's simplify each vector. So when we multiply 5, 2 by 4x plus y over 22, we are going to get, multiplied by 5, you'll get 20x plus 5y, and multiplied by 2, you will get 8x plus 2y. And now for the second vector, we will multiply negative 1, 4 by the scalar minus 2x plus 5y. So when we multiply by negative 1, we will get positive 2x minus 5y. And when we multiply by 4, we are going to get negative 8x plus 20y. So let's put these two vectors together. In the x component, we will get 20x plus 2x, so that's 22x, 5y, and minus 5y, so those cancel. So we will get 22x over 22x, that's just x. And similarly, in the second component, we get 8x minus 8x, so those cancel, and we get 2y plus 20y, that's 22y. So we get 22y over 22, and we get, indeed, just xy. All right, so there you have it. Every vector xy in R2 can be written as a linear combination of two vectors 5, 2, and negative 1, 4. So the span of those two vectors is all of R2. All right, so that is our video for today, the span of a set of vectors in R2. Our next vector will be about the span of a set of vectors in R3. So I hope to see you there next time. Enjoy the rest of your day. Thank you for watching this video.